Okay, today we're going to start looking at logic gates, and there are 6 different logic gates that we need to look at. There are 3 that are key: the not, the and the or. The reason why computers use logic gates is we've got the maths behind logic, and we can very easily simulate them or create them by using transistors, which is solid state technology, which means they're very reliable transistors, and they allow current to flow through them under certain situations, and so that allows us to give us like an on or an off situation. It's a very efficient switch. So the first 3 which we'll look at, the not, the and the or. The not takes a single input and we'll flip it, invert it. So true, if you like, becomes false, false becomes true. We often refer to, when we talk about logic gates, we'll refer to either true or false, 1, 0, on, off, the 2 states that we can possibly have. And takes 2 inputs and it returns a single output. If both inputs are true, then the output will be true. Otherwise, your output's going to be false. Or takes 2 inputs and it returns a single output. If either of those inputs are true, then the output will be true. And these 2 work very similar to you would have in an English statement. The book is red or it is blue. So you know the book is one of those 2 colours. Okay, so this is some logic gates that have been set up. This is the not, this is the symbol for and this is the symbol for or. If I start the simulation, this one here, this is the not. We've got nothing coming through here, but our output is on. The light bulb is on. If I turn the switch off, there's current running through here as an input into the not gate, but the light bulb now comes off. Okay, so that just inverts our results. Over here is the and. So this, as we said, needs both inputs to be on before the light bulb itself will go on. So I can put this one on, still no light bulb. I can put this one on, still no light bulb. But when I put both of them on, we get a true coming out. We get the light bulb coming on. This one, this is the or. And for or, I said we just need one of them to be on. So if I turn this one on, the light bulb goes on. If I turn this one on, the light bulb goes on. And if I turn both of them on, the light bulb is on. So that's how the 3 basic logic gates work. This is what their symbols look like. However, for IB, if you're ever asked to write a logic diagram, then you can just do a symbol, a circle with the logic gate name inside. So you do a circle with or circle with and, circle with not inside it. Okay, so those are the 3 main ones. There are 3 other ones which we'll go into. The NAND and the NOR, those are very, very similar to AND and OR. They've just then inverted afterwards. So a NAND is not AND, and a NOR is not OR. So the NAND is false when both inputs are true. The NOR is true when both inputs are false. The XOR, now this is a little bit different, it takes a little bit of time often to get your head around it when you first see it. Again, it takes 2 inputs and returns a single output. It is true if both inputs are different. It is false if both inputs are the same. So it's going to be the same as A or B, but not both. So if A is true, light bulb goes on. If B is true, light bulb goes on. But if both A and B are true, then no, that's a false. Okay, so that's the 6 key logic gates that we need to consider on this course. The XOR can be quite powerful. We'll, I think, see at some later point. It's possible to simulate those just from AND, OR, and NOT, but it can be very convenient if we can actually build an XOR by itself. Same with the NAND and the NOR. We can build those by themselves using transistors, and often much more efficiently than if we would just use combinations of AND, OR, and NOT.